So remember from last class, I guess a week ago now, we were talking about a couple of specific synchronization problems. So remember we first were talking about the reader-writer problem, where you have shared data that you have readers and writers accessing it. And remember the objective was we wanted to allow multiple readers to be reading the data simultaneously, but only one writer at a time, and then readers and writers could not go at the same time, to prevent a writer from writing while another writer is trying to write, so on and so forth. And so we talked about how we can actually solve that problem, but in practice, you can generally, as a programmer, just use a read-write lock, which is sort of a very standard pattern for doing the reader-writer problem, which lets you take either a read lock or a write lock. And then we talked about dining philosophers, which was our sort of toy example for the problem of when you need multiple resources in order to perform a task. So remember the question there was, you have a bunch of people around a table, each one of them needs two chopsticks in order to eat, but the chopsticks are shared, so you can potentially run into a situation where you can't get all of the resources you need in order to be able to proceed. So what we talked about last time is going to sort of frame what we talk about today, which is going to be specifically going into more detail about deadlocks. But before we jump into that, I just want to mention, I mentioned a few of these last time, but just to give you a sense that the types of problems we looked at are not just sort of toy examples for studying OSs or whatnot. They actually are used in real applications. So to give you some ideas, something like producer-consumer, a good example of that is something like maybe your browser is streaming video or streaming audio. And typically what you're going to have there is you're going to have some shared buffer of data and some thread that is receiving data over the network, from YouTube or whatnot, and basically putting it into that shared buffer. That's essentially the producer. And then you may have a consumer that's actually reading data out of the buffer, decoding it and actually displaying it in your browser. So that would be an example of producer-consumer. Another example that I mentioned last time was with web servers. And so remember, one of the ways that web servers are often actually designed is you have some producer thread that's essentially listening for requests coming in from clients, page requests. And so those are getting put into a shared queue of requests that are waiting to be serviced. And then you have some other worker threads that are actually consuming off that queue and actually going ahead and sending the page back to the client. So that's another example of producer-consumer. For the reader-writer problem, a lot of examples here, just about any kind of application where you have something like a database, where you have potentially large numbers of concurrent readers and writers, and you of course want as much concurrency as possible. So if you have a banking system where obviously balances might be getting updated, but you also have maybe you have a background thread that's calculating interest or whatnot, you might have concurrent reading and writing going on. And then dining philosophers, again, this is essentially any kind of problem where you have cooperating processes that are sharing resources. So any kind of thing where you have multiple resources that need to cooperate. So for example, maybe you're booking a travel package, and so you need to cooperate between a hotel, an airline, or a car rental database. So these types of problems do actually show up a lot in practice. So today we're going to be talking explicitly about deadlocks, which is a term that we've used several times before, but haven't sort of really been explicit in what exactly deadlock means. So we're first going to talk about what is a deadlock. Then we'll talk about what are the necessary conditions in order to actually have deadlock. And then we'll talk about sort of three different approaches to dealing with deadlocks: detection, prevention, and avoidance. And we'll talk about what each of those terms mean. So first, let's talk about what is a deadlock. So someone give me sort of a very intuitive definition of what a deadlock is. So if I say your program is deadlocked, what does that mean? Yeah. It can't move forward. Right. It means your program is stuck. And typically, we're talking about concurrency, synchronization here. So typically what that means is that you have, a couple of threads or something that are stuck, that cannot make progress. So, formally, a deadlock is a condition where you have multiple threads, and they're waiting for some event, but that event that they're waiting for is actually generated by those same threads. right? So the idea here is that if you have threads that cannot proceed until some other event happens, but that event is not going to happen because your threads are waiting on some other event, then there you have a deadlock. None of your threads are ever going to make progress because those events will never actually happen. And so let's give a very simple example of this. Maybe we have two processes and they're working with, say, a disk or a printer, a disk and a printer. And so those would maybe be shared resources that they need to take a lock on or something. So process A may call printer.wait to take control of the printer, and then call disk.wait, take control of the disk, copy from the disk to the printer, and then release that. Process B may do the same thing in the opposite direction. So what could happen here to cause a deadlock? Yeah.
So if you have the two threads alternate in the following way.
Right. Remember, the whole problem here in all these synchronization questions is that we don't know exactly how the CPU scheduler is actually going to schedule things. So we essentially can make no assumptions about the order in which things run. So what could happen here is process A and B are running concurrently. Process A calls printer.wait, and let's say right after that happens, we switch to process B calls disk.wait. So now process A has control of the printer, process B has control of the disk, and now process A goes to grab the disk. It's held by process B, so it blocks. Process B goes to take control of the printer, which is held by process A, so they block. And assuming there's not, some other mechanism that's going to actually break these processes out of that, they're essentially stuck forever. They're deadlocked. They cannot make progress because process A is waiting on disk.signal, process B is waiting on printer.signal, and those are only happening within the deadlocked threads. Right? So that's exactly this definition. They're waiting on events from within the deadlocked threads. So there's going to be some terminology that we use when talking about deadlocks. So we already talked about what a deadlock is. So there's basically three approaches we're going to talk about to dealing with deadlocks. The first is deadlock detection. So this is the idea of if a deadlock happens, if you didn't prevent a deadlock from happening, if you do actually have deadlock threads, you can try to figure out that you have a deadlock, or at least a possible deadlock, and then essentially do some kind of recovery to break your threads out of the deadlock. So that's one approach. A second approach, deadlock prevention, is where we're going to essentially impose some restrictions on how programs can operate and acquire resources. And by imposing those restrictions, we're going to prevent the possibility of a deadlock from ever occurring. So then we don't need to worry about deadlock detection because we are ensuring that a deadlock will never actually happen. And then a third approach is what we're going to call deadlock avoidance. And this is subtly different from deadlock prevention. But the basic idea here is that in deadlock avoidance, this is going to be a runtime approach. So at runtime, programs are executing, threads are executing and asking for resources. And essentially, whenever you're asking for resources, we're going to run some algorithm to determine if giving you that resource might cause a deadlock. And if it will, then we won't give you that resource. So essentially, prevention is where we're saying you're just going to have to write your program so that deadlock never occurs. Avoidance, we're going to say we're going to run some algorithm so it's not as restrictive to you as a programmer, but we are at runtime going to prevent deadlocks from ever occurring. Now, one other term that seems similar that we've talked about before is starvation. Now, starvation is not the same thing as deadlock. So who can tell me what's really the difference between starvation and deadlock? Yeah. Right. Deadlock is when your threads cannot continue. There's no way that they can continue, regardless of the load on the system. Starvation is essentially an issue where your system is still making progress, but it's essentially busy making progress on some other threads or processes. So a thread that is subject to starvation may never make progress just because the system is busy with other things. But if the thread actually could make progress, then that's starvation as opposed to deadlock where you cannot make progress at all. Yeah.
Can you give an example of prevention versus avoidance?
That's what we're going to be talking about. So we'll get to that. Yeah. But I mean, essentially, avoidance is where you're doing it all at runtime, where you're requesting your programs are running and they're requesting resources, and when they request resources, we're going to figure out whether that might cause a deadlock or not. Versus prevention, we're basically going to have some restriction on the way that your program, the way you can write your program, basically. And if you write your program following this restriction, then you know that when you actually do run your program, there won't be any deadlocks.
So like, in unthreaded programming, deadlock prevention.
An unthreaded program.
Like,
Well, if you have
a program without threads, would that
yes, if you had a program that had no concurrency, there are no synchronization issues, then clearly your program can never have a deadlock, right? Because deadlocks are occurring when we're using synchronization and things get blocked waiting for other events. So if there's no, if there's no cooperation between threads, or you're not, even using threads, then clearly deadlock is never going to occur.
So then on the other side of the point, like if we're doing stuff to make sure that no one thread can ever enter like a critical section, is that also prevention or is it?
Yes. Yeah. Well, and we'll get to that. You're all good points that we'll talk about. Other questions before we move on? Okay. So before we talk about the detection, prevention, and avoidance, first let's talk about what are the necessary conditions for deadlock. So we have some sort of intuitive understanding of what causes a deadlock, but more formally, there are basically 4 conditions that all have to hold in order for a deadlock to be a possibility. This doesn't necessarily mean a deadlock will occur, but but in order for a deadlock to be able to occur, you must have all 4 of these conditions. So the first is mutual exclusion, right? And we all know what that is. That's where you have a thread that is holding a resource that can't be shared, right? So if you don't have mutual exclusion and resources are all shareable, then clearly you're never going to have a deadlock. Second condition is hold and wait. So that's where you essentially have the condition that a thread cannot proceed because it's waiting for some other resource to become available. So, in that previous simple example, we had either the thread was either waiting on the printer or waiting on the disk while holding either the printer or the disk, respectively. Third condition is no preemption. So that's where a thread can only release a resource when it chooses to. You can't have some other thread come in and force the first thread to release its resource, right? Because in the previous example, if we were able to force one of the threads to give up the printer or the disk, then we might still be able to proceed. So you need to have no preemption. You can only release resources voluntarily. And then the fourth condition is what we call circular wait. And this is where you have essentially a bunch of threads that are waiting in a circle in order to proceed. So to give you sort of an intuitive sense of this, just returning to this example, right, we have process A here. So we have process A here and process B. And process A is potentially waiting on process B in order to proceed. And process B is potentially then waiting on process A to proceed. Right? So it's essentially a circular wait where you have a cycle of threads that are waiting in turn in order to be able to proceed. And we'll talk a little bit more about what that is. So these first 3 are sort of design decisions in that we sort of all want all of those things. Those are all useful in the way we write programs. So this circular wait condition is sort of the most interesting one that we can talk most about. So let's talk about how we can actually first detect deadlocks by focusing on this notion of circular wait. So to do this, we're going to introduce the idea of a resource allocation graph. So remember, in a problem like this, we have resources and we have threads. So let's just say we're going to number our resources, R1 through Rm. You're going to have some M resources. And T1 through Tn are N threads. And so we'll make a resource allocation graph like this, where you have, in this case, R1 through R4, you have 4 different resources. T1 through T4, 4 different threads. And essentially, we're going to put in edges here determining who holds resources and who's waiting on resources. So when you have an edge going from a thread to a resource, these are directed edges. So an edge going from a thread to a resource means that the thread owns that resource. The thread has acquired that resource. So, in this case, T2 has acquired R1, T3 has acquired R2, so on and so forth. And then an edge, from a resource to a thread means that, I'm giving this reverse. So an edge from a resource to a thread is an assignment. So that means that T3 is holding R1, T4 is holding R2. Whereas an edge from a thread to a resource is where the thread wants that resource. So that's a request edge. So in this case, R1, the resource, is assigned to T3, but T2 wants it. So T2 is waiting on R1 to become available. Questions on that? So in this case, T1 doesn't want or have anything. T2 has R3 and wants R1, so on and so forth. Questions on how we set that up? And by convention, we're just using circles for threads and squares for resources. So what can we say about this? Well, what we can say is that if there's no cycles in this graph, then no deadlocks can exist, right? And this is essentially the idea of circular weight, where, well, let's start. Is there a cycle in this graph? Yeah, there's a cycle in this graph. We have T2, R1, T3, R2, T4, R3, back to T2. So we do have a cycle in there. So there could be a deadlock here, right? Because we essentially have, T2 is waiting on this, T3 is waiting on this. They're waiting in a cycle, and if all of them are just blocked waiting for that resource, then this is a deadlock. Right? But let's say, for example, that we remove this edge. So if we remove that edge, what does that mean? That basically means that T4 is no longer requesting T3. T4 is no longer requesting R3. So let's say we remove that edge. Are we still going to have a deadlock? So why are we not going to have a deadlock if we remove that? How could this resolve? Right, so remember, we still have threads, waiting on various resources in order to be able to proceed. But if we don't have this, how can these threads complete their work and all the work gets done? Yeah.
When thread 4 is run, after thread 4 is run, and it's no longer using resource 2.
Right.
So T3 can use it, and then
right, exactly. So if we remove this, then T4 is no longer waiting on T3. T4 is not waiting on anything anymore. So T4 can go ahead and run. Once T4 is done, it was allocated T2, so it's going to, R2, so it's going to give up its resource, R2. Once it gives up R2, T3 can now take control of R2. T3 is now waiting on nothing, can go ahead and do its work. It will release R1, so on and so forth. Essentially just work back through the chain, and everyone is actually going to be able to execute. Make sense? Right, so the key point here is that in a graph like this, if we have a cycle, we could have a deadlock. But if we don't have a cycle, then you can always complete the work, because at the end of the chain where the cycle is, where there is not a cycle, you always have a thread that can actually do its work and then give up its resources, and then you just work backwards. Questions on that? Okay. So note that we did say here, if a graph has a cycle, a deadlock might exist. So anyone have any idea why you might not actually have a deadlock? Yeah. Okay. Yeah.
Someone else has requested your resource, and you can send it to them before we get the resource.
So I think you're saying if you maybe release a resource before you've gotten all the resources that you want. Yeah, that could be the case. I mean, the way we've discussed this here, we're sort of saying that you know are sort of trying to gather all the resources you need in order to proceed. So in general, you're not going to give up a resource and still be wanting another resource in order to run. But that's a good idea. So the way that a deadlock might not exist here is we're sort of assuming here that there's one copy of each of these resources. And that might not actually be the case. We could have a situation where you have multiple interchangeable instances of a resource. So let's say you have like a bank of printers, and your thread needs to use a printer, but it doesn't care which one. You might have multiple printers. So we can essentially extend this idea of a resource allocation graph to account for the fact that you may have multiple copies of a resource. So this is essentially the same example as before, except now we have 2 interchangeable copies of resource 3 and 3 interchangeable copies of resource 4. Otherwise, it's the same. We have still 1 copy of R1 and 1 copy of R2. So in this case, we have a situation where a cycle does not necessarily indicate that, that a deadlock exists. So let's look first at this case. So here we have, essentially when you are requesting a resource, you don't care which instance of the resource it is. You're just pointing, so you know T4 is pointing to R3, but not any specific piece of R3, not any specific instance. Of course, when you actually have a resource assigned, you have a specific instance of that resource. So this instance of resource 3 is assigned to T2. This instance of resource 3 is assigned to T3. So what do people think? Do we have a deadlock here? So is anyone going to be able to make progress here? Obviously, we can, T1 can make progress because it's sort of not cooperating with the rest of them, but can anyone else make progress here? Yeah. Remember, we're again sort of assuming here that the processes are all trying to get all of their resources that they want before they can proceed. So yeah, it's true that maybe in the course of running your program you are giving resources up or allocating more, but we're essentially assuming that what one of these edges means is that you have asked for that resource right now, and you need that resource in order to be able to proceed. Right? So this is like the dining philosopher's problem, where you get one chopstick and you get the other, and you need to get both of them before you can actually do anything. So every time we have one of these request edges, essentially the thread is waiting for that resource to be allocated to it before it can actually proceed. So given that, can anyone make progress here? Right. This is still a deadlock. Right? Because all of R3 is assigned, but T2 and T3 are waiting, and we have this cycle. We actually have a couple of different cycles in here. So this is still a deadlock. But now let's consider this scenario where we have, say, 3 copies of R3. That's the only difference here. So now what do people think? Do we have a deadlock here? Yep.
No, T1 will run until it releases its copy of R3 because it's not dependent on anything, so then T4 can get that.
Right. Yeah, so here we have a 3rd copy of R3, currently assigned to T1. So, in this case, all of T2, 3, and 4 are all still blocked. But T1 is not waiting on anything. Thread 1 can finish and release its copy of R3. Now we have a copy of R3 that can be assigned to T4. So now T4 is not waiting on anything, and essentially, the cycle has been broken. So now T4 has everything it needs, and essentially no more cycle, so no more deadlock here. Everyone see how that's working? right? So this is how you can have a cycle, but with these, when you introduce the idea of multiple interchangeable resources, that doesn't necessarily mean you have a deadlock. Now, in the previous case, if we're assuming that you only have one copy of each resource, then a cycle does definitively mean you have a deadlock. But in general, we're not going to make that assumption, so a cycle only means there could be a deadlock, but not that there necessarily is a deadlock. So, in general, when you have multiple instances of these, you would need to do some further analysis to determine whether there actually is a deadlock. You can just fairly easily say whether there might be a deadlock. Questions on that before we continue? Okay. So, one thing we can do is we can simply look for these deadlocks, or at least potential deadlocks, and then try to correct it. So what that means is if we have this resource allocation graph, we can look for cycles, and whenever we see a cycle, that says there might be a deadlock. So what can we actually do? We can then just break the cycles. So a few different ways we could possibly do that. You could do things like just kill all the threads in the cycle, just terminate them all. Obviously, there's no more deadlock if you do that. Probably not the best approach. You could do something a little less extreme. You could terminate threads one at a time. Because remember, if you start terminating threads, probably sooner or later you're going to break the cycle, and then everything will start moving again. But also not ideal. You can also start preempting resources to essentially forcibly give up resources. And that's actually something that's often done in database transactions, where you have sort of the idea of a commit and a rollback, where if you get to some state where you can't proceed, you essentially roll back the database transaction to the previous state before you acquired all of your resources. So we could do things like that. Obviously, none of these are exactly ideal. Now, one problem we have is that to actually detect cycles takes order n squared time in the number of threads and the number of resources. So when you have a lot of threads and a lot of resources, which is certainly a possibility, it can actually be pretty expensive to actually go in and detect cycles. So one question we have to decide is how or when are we actually going to run some cycle detector to actually try to detect a possible deadlock. A few different possible approaches. You could do that whenever you're granting a resource, right? Because that's essentially whenever your resource allocation graph is changing, or alternatively when a resource request can't just immediately be filled. You could also do things to try to account for the fact that detection could be expensive. You could do something like do it on a regular schedule fairly infrequently, or when your CPU is fairly idle. So a few other approaches that you could use. But in general, current OSs don't really do any of this. They essentially just leave it to the programmer or application to make sure deadlocks don't occur, right? Because when you're doing this, your OS is basically having to decide a lot of questions about what thread should I terminate, what resource should I release, and these are not the kind of questions that in most cases your OS will be able to give you a good answer to. Right, you as an application programmer are in a better state to actually deal with a potential deadlock than the OS. So most OSs are essentially just leaving it to the programmer. So let's talk then about deadlock prevention. So this is essentially asking the question, how can you as a programmer, given that the OS is not going to detect and break deadlocks for you, how are you actually going to write code that is not going to have deadlocks? Now remember, we talked about these 4 conditions: mutual exclusion, hold and wait, no preemption, and circular wait. And in order for deadlock to be possible, you have to have all of those conditions. So what does that suggest a decent way to ensure that you never have a deadlock is? If you need to have all 4 of those conditions in order to have a deadlock be a possibility. Yeah. Right, only use 3. Basically, if you break one of these constraints, if one of those conditions is not true, doesn't matter which one, if any one of them is not true, then deadlocks are impossible. Because remember, you need to have all 4 of those conditions in order for deadlock to be a possibility. So essentially we can consider, how can we not have one of these properties be true? So mutual exclusion, we could just say, we're going to have all of our resources be shareable. Not too useful, we obviously have been talking about all the synchronization stuff in the context of mutual exclusion being a good thing, right? So we don't want to just sort of say, well, we won't have that anymore. Everything will be shareable. Many resources can't, not all resources can easily be shared, so not a great option there. Hold and wait, remember, is the idea of holding a resource and waiting for another one. So you could impose that that could never be the case by saying, for example, a thread cannot hold a resource while it requests another. So an easy way to do that is whenever you need more resources, you essentially have to give up all the resources you currently have available and request, your new set. Right? So let's think back again to the really simple printer and disk example. If one thread is holding the disk and wants the printer, if it has to give up the disk first, then the other thread is going to be able to continue. The thread that just gave up the disk will request both of them at once, and because the other thread was already holding the printer, it won't be able to proceed. So that essentially prevents a deadlock from occurring if you are saying you don't have hold and wait. So that's one option. Also not ideal because it's kind of restrictive, in that you have to request everything you need all at once, and if you decide later you need something else, you have to give it all up. So that's also not ideal. We could, of course, say, let's let resources be preempted. If you want resources that can't be allocated, the OS just releases the resource. Also not great if you essentially have no guarantee that resources you're holding are actually going to, stay allocated to your program. And also, you could consider a case where some resources is not really clear how you would preempt them, something like a printer. So essentially, the most useful way to do this is by looking at this fourth condition, circular wait. So if we want to impose that, if we want to force circular wait to never be a condition, one very easy way we can do that is essentially taking all of our resources, giving them some numbering, and then ensuring that you only request resources in, say, ascending order. So, back up. So, if we're using this again, let's say, we have two resources, the printer and the disk. And so we could say, printer is going to be resource 1, disk will be resource 2, and you can only request them in order. Then, a deadlock is not going to occur because, the whole problem here is essentially that we've swapped the order of requests. So if we're doing that, then this would sort of no longer be valid code because it's requesting a higher resource before a lower resource. So if you're always requesting resources in order, then is a deadlock ever going to, is a deadlock a possibility? Because if a deadlock was a possibility, then what would that have meant if you have this order of resources? Because remember, we have this circular wait where a thread is essentially waiting on a resource that has already been assigned to some other thread, and that thread is waiting on a resource assigned to the first thread. So essentially what that means is that you must have had a case where a resource was requested out of order. That's the only way that you could actually get a cycle. So if you impose this ordering, cycles are never a possibility. So, questions on this before we move on? Right, so idea behind prevention is you're just going to write your program in such a way that one of the 4 conditions will not hold. And if you're ensuring that one of the 4 conditions will not hold, then deadlocks are impossible. And in practice, this circular wait is sort of the least damaging one to do. So you can do something like imposing this ordering. Still not ideal because it means it's fairly restrictive in how you can request resources. So still not great, but that is a possibility. So next we're going to talk about deadlock avoidance, which is basically going to ask the question, how can we prevent deadlocks without imposing, really restrictions on how our programs can actually be written. So, and then we're going to talk about one specific algorithm, which is called Banker's algorithm. That's a way to actually do deadlock avoidance. So, the main idea that we're going to need is we're going to need some notion of resource reservation. So what that means is that threads are going to have to say in advance what resources they might need in order to complete. That doesn't mean they're requesting them right now. It just means they're essentially saying, I may need these resources in the future. And then by requesting, by essentially saying up front what resources you might need, we'll be able to do some reasoning about how to assign resources in order to prevent deadlocks. So the basic idea is that if we have some sequence of some number of threads, and we know that those threads might ask for some set of resources in the future, we want to be able to essentially say, in the current state, given resources that are currently assigned, as well as resources that threads might want in the future, is it ever possible for a deadlock to occur? Because what we're going to see is that we can often say that we can always assign the resources that a thread might need in order to allow it to make progress. So let's look at an example of this. So let's say we have, say, 12 tape drives. This is sort of an old example, but tape drives are often used for a long-term archiving. So let's say you have 12 tape drives, right? So these are 12 instances of the same interchangeable resource, and we have 3 threads, T1, T2, and T3 that are competing for them. And let's say that at the current time, 11 of the tape drives are allocated to the threads, and so that there's one that's available. So that looks like, and so each of the threads declares up front the number of tape drives it might need in order to complete. So, T1 might need 4 drives, T2 might need 8, T3 might need 12. We have 11 of the drives currently assigned, so let's say T1 has 3, T2 and T3 each have 4. And then, the difference between what they might need and what they currently have is essentially what they might request. Right? That doesn't mean they necessarily will request it, but it's what they might request. So essentially what this is saying is that T1 will never need more than 4 tape drives in order to actually do its work. So the objective here is essentially when a thread is going and requesting more resources, we want to ask the question, is it actually safe to give those resources to the thread, or is it possible that that might lead us to a situation where we have deadlock? So, actually, let me back up for one second. So basically, the idea is that a current state is going to be considered safe if you can basically make an ordering where all of your threads will be allowed to complete, and you can guarantee that there's going to be no deadlock. So, for example, in this case, we have T1, T2, and T3, and we have some sequence where all of the threads are going to be able to complete. So remember, we have 1 tape drive available. So what's the worst thing that could possibly happen here in terms of allocating resources? Remember, we don't know what each of the 3 threads will request except for this. So what's the worst thing that could happen? Yeah. Well, just in a sort of general way, essentially the worst thing that could happen is that every thread requests all of the resources it might want. Right? Because that's the worst situation where every thread requests the maximum number of tape drives. So supposing that happens, T1 wants 1, T2 wants 4, and T3 wants 8. So we're essentially saying this state is only safe if we can actually handle a situation like that without running into a deadlock. So how could we actually handle a situation like this? If we have 1 tape drive available, what's the first thing we can do? Yeah. Right. So we have 1 tape drive open. We can give it to T1. T1 now has, the maximum number of tape drives it could need. It's never going to request more, which means T1's now going to be able to complete. Right? It has everything that it might need. Once T1 completes, how many tape drives do we have available? 4. Right. Because T1 had its maximum, which is 4. T1 completes and now has released its 4 drives. And now what can we do? Right. Now T2 wants 4, so we give the 4 drives to T2. T2 completes, and now how many drives do we have open? Now we have 8. T2 had all 8. It releases them, and now T3 can take all 8 and complete. Right? So this state is safe. And what we mean by that is simply that there is a sequence whereby we can complete all of the threads and guarantee that there's no deadlock given what is currently allocated and what they might request. Make sense? So there, we could do it in some other order that might not be good, but as long as there is a sequence that we can assign things to guarantee that deadlock will not occur, then it's still a safe state. So this state is safe. Make sense? So now let's look at a different example. So let's say T3 requests one more drive. So supposing we just go ahead and allocate that one drive to T3. So what's now going to happen is T3 has five drives in use instead of 4. And of course now it could only want 7. But now how many drives are available? We had 1 previously, so now how many are available? 0, right. So there's no drives available, so is this safe? Right, it's clearly not safe because there's essentially no way we can ensure that these will complete safely. Now remember, it's still possible they might, because remember, we're only saying here, these are the maximum number of resources the thread might request. No, it's possible that T1 will never actually request its 4th drive and will complete, in which case we might be able to make progress. But we essentially can't guarantee that anymore, whereas in the previous state we could guarantee that it was safe because there was a sequence that would allow us to make progress and avoid deadlock. So essentially the idea here in deadlock avoidance is if, in this case, say T3 requests one more drive, that would lead us to an unsafe state, right? Because that would lead us to this state which is not safe. So instead of doing that allocation, even though we do have the drive available, we're going to force T3 to actually wait. And we'll force it to wait until giving it that drive would still result in a safe state, right? Because the whole point is we never want to end up in a state like this where a deadlock is possible. As long as we're always moving from a safe state to another safe state, then deadlocks we can always avoid a deadlock. Make sense? So that's really the basic idea of deadlock avoidance, is that when you're requesting a resource, we only want to give it to you if we can ensure that doing that will not open us up to the possibility of a deadlock. Make sense? Yeah. Yeah, this is deadlock avoidance, which is, this is happening while your program is running. I think I just said deadlock avoidance. We're going to talk about a specific algorithm called Banker's algorithm that's actually used for doing this. But yeah, I think maybe you're thinking of resource reservation, right? So the main idea here is that we're introducing this notion of saying in advance what resources you might want and using that to be able to do deadlock avoidance. Other questions before we continue? Okay, so let's look at one way of doing deadlock avoidance by returning to our idea of a resource allocation graph. So remember, again, we have our threads and our resources and request edges and assignment edges. And we're going to introduce now a third type of edge, which are these dotted edges, which are going to be claim edges. And so the idea there is that it's a resource that might be requested in the future, but is not currently requested right now. Right? So the idea here is that T3 and T4 have declared up front that they might request R2, but are not requesting it currently. Right? So this is essentially the idea we just introduced of resource reservations, saying they might use R2, but are not using it right now. So what happens is, let's say that T4 actually, at some point in the future, requests R2. Right, so this is currently a claim edge, and R2, you'll notice, is not currently assigned. So let's say that T4 requests R2. R2 is available, so we could just give R2 to T4. Now, if we do that, then what happens to this edge? Yeah. If we do that, then this edge becomes an assignment, which means it flips, and it's now going to be a regular assignment edge pointing from R2 to T4. Now, if that happens, anyone see what just happened to the graph? Yeah. Right. If that happens, we just introduced the cycle. Right? So here, there is no cycle. But if we make this assignment, we flip this edge, and now we have a cycle. So remember, that doesn't necessarily mean we have a deadlock here, because this is still just a claim. This is not an explicit request yet. But if this were to become a request, then we actually would have a deadlock. It would be the exact same as we had previously, where we have this cycle of threads waiting on each other, and there we have a deadlock. Right, so this is essentially the idea of the unsafe state again, where if we assign R2 to T4, we now have an unsafe state because if T3 goes ahead and requests R2, now we have a deadlock. People see how that works? Now, how about T3? What if T3 requests R2, and we give R2 to T3? Yeah. Right. That actually is still a safe state. Because if you do that, you take this edge and flip it, and make it a regular assignment edge, you still don't have a cycle here. Right? Because now T3 has everything it needs, and it'll complete, and then again, everything else will be able to run. You know, even if T4 goes ahead and requests R2 afterwards, that's okay because you will still not have a deadlock, no cycles. So the idea here is that, you know, a cycle in this extended resource allocation graph is exactly that unsafe state. So if we want to avoid that, all we have to do is, whenever we're doing an allocation, if that allocation, whenever we have a request for a resource, if giving that resource would result in a cycle, then we just deny it. Right? So in this case, if T4 asks for R2, we won't do that because that will create an unsafe state. If T3 asks for R2, we will do that because that's still a safe state. Questions on that? Right, so the whole point is we only want to be moving, you know, from safe state to safe state, never into an unsafe state. Now, again, this solution is, you know, assuming that there's one copy of each resource, which is, you know, not true in general. So next we're going to look at Banker's algorithm, which is basically the same concept of we want to be moving from safe state to safe state, but it's going to allow us to handle actually multiple instances of a resource. So the basic idea is going to be the same here. You know, each thread needs to provide advanced information about what resources they need, and also, because we have multiple copies of a resource, how many of each resource they need. And then, of course, you know, you can't request more resources than you actually have available. And you know, what the algorithm is actually going to do is, when you make a request for a resource, the algorithm is going to decide, you know, whether doing that leaves you in a safe state, and therefore will either give you the resource or make you wait. So let's look at some pseudocode for how we can actually do this. So this would be sort of an example if you were doing it in Java using monitors. So we're going to have, you know, n threads and m different resources. So, you know, these are just T1 through Tn and R1 through Rm. And remember now, since we have multiple copies of each resource, we're also going to have, you know, this array available, which is going to be, for every resource, how many copies of that resource are currently available. And remember, this is going to, you know, change over time because the number of resources available at any given time might be different. Then we're going to have three matrices. So first we're going to have, you know, the max number of each resource that a thread might request. Right? So this needs to be a matrix because for each thread there are, you know, m different resources that it could request, and it's saying how many of each of those m resources might you request. Then you have, you know, the current allocation of your resources. So each thread is currently allocated some number of each of those M threads, each of those M resources. And then you, of course, have some number of each of those resources that a thread might need in the future. Right? This is the same idea we were talking about with the tape drives. We're just sort of generalizing the idea of multiple different resources. So what's going to happen is when you request to be allocated a resource. So in this case, we're going to have, allocate, we're going to have some thread I that's making some request, and its request is essentially saying how many of each of the resources do I want right now. So, maybe I want 2 copies of resource 1 and 5 copies of resource 2, and that's my request. So that's why it's, it's an array of requests. So the first thing you're going to do is we need to say, is this an allowed request? Are you requesting more than your maximum allocation? Right? Because the need vector here is essentially how many resources you have not been allocated that you still could. So if you're exceeding that, then it means you're requesting more than you declared, so that's an error, that's not allowed. Of course, if you're requesting more than the number of resources that's currently available, then obviously you have to wait, you can't proceed immediately. But so if you get past that point, it means there are enough available resources to give you the ones you requested. Now we need to actually check if giving you those resources would lead to a safe or an unsafe state. So the idea here is, we're basically going to assume that we gave you the resources. So let's just assume that you did get that allocation. So what would happen is, the available resources are going to be decreased by whatever you're requesting. These are just doing a subtraction of 2 vectors. Each one of those resources is decreased by the resources that you're requesting. And then, of course, that increases your current allocation, decreases is your possible future needs. And then we're going to check if this is a safe state or not. And if it's not a safe state, we're just going to sort of undo what we just did and wait. If it is a safe state, then everything's fine. So that's the basic idea. And of course, the main thing here is we need to actually determine whether this is a safe state or not. So the idea here is, again, what we talked about previously. The idea is we want to look for some sequence of threads that will allow everyone to execute, even if the worst possible thing happens of everyone requesting the maximum amount that they're allowed to request. So we want to find some sequence that will allow everyone to complete, even if everyone requests everything that they're allowed to. So the idea here is we're going to track the resources that are available to do work for the thread that's running. And initially, that's just going to be the available resources. And then we're going to track each thread whether it's actually finished or not. Right? Because if it's not finished, essentially that means it's still blocked waiting for resources so that it can proceed. So the idea is that we're essentially going to look for some thread that has not yet done its work and that requires less than the number of resources that are currently available. Right, so what does that mean? If finish I is false, then that means the thread hasn't run yet. And if need is less than work, then that means that the thread actually can go ahead, get everything it needs right now and run. So if that's true, then what's going to happen to the thread? What can we do with the thread? If all the resources that are available for it to run are available, then what should we probably just do? Yeah. Right. Yeah, so we can just give all those resources it needs to that thread. It will run, and then it will finish. And once it's finished, all of the resources that have been allocated are now available. Right? So the resources that are now available for subsequent threads have been increased by whatever resources were allocated to the thread that just ran. Does people see how that's working? So we're essentially just doing this over and over again. We're finding a thread that we have sufficient resources to let it run. assuming that it will run to completion, release all of its resources, now there's even more resources available for the next thread that we could run. So all this is doing here is it's essentially building up a sequence of threads that we could run one after another, and that sequence will guarantee that there's no deadlock, because of the assumption that a thread will never request more than the number of resources that it declared up front. Now, if every single thread finishes, which means finish I is true for all I, then what does that mean? That means we're in a safe state, right? Because we found some sequence that allowed everything to complete. Now, if that wasn't the case, then what did that mean? Yeah. Right, perfect. So it means that we got to some point here where we had a thread that, or rather we couldn't find an I. So that means all of the threads we have remaining that have not run, we can't actually guarantee that we have enough available resources to run them. So essentially, we cannot guarantee that there won't be a deadlock. So in that case, we come down here and we return false, meaning this is not a safe state. We cannot guarantee that there won't be a deadlock here. Yeah.
So, is this algorithm used for proving whether or not safe state exists?
Well, this algorithm is saying whether the current state is safe or not, right? So we're not actually. It's sort of running it's almost like you're running a simulation of what would happen in the worst case if everyone requested the maximum number of resources. Because if that happened, you want to be able to say definitively, I can still handle it without there being a deadlock. Right? Because if something requests less resources, that's a good thing, right? That never actually makes it more difficult for you to ensure that everyone can do work. Right? Having more resources available is never harmful. So we're just saying, if the worst thing happened right now, can we still guarantee no deadlocks? And if we can guarantee that, then this current state is safe. If we can't guarantee that, the current state is unsafe. So remember what we were doing back here is we were essentially assuming we were giving the allocation that was requested, and then checking if it's a safe state, given the updated available allocations and possible future requests. And then if that's not a safe state, we basically just roll back these changes and don't do that right now. But if it is still a safe state, we can go ahead and actually allocate those resources. People see how this is working? So let's look at a more concrete example of doing this. So what we have here is we have, say, 4 different. Here we're using processes, but processes or threads we're sort of using interchangeably here. And we have 3 different resources, A, B, and C, and of course multiple copies of each, right? Because that was basically the whole point. And so up front, each process/thread is declaring how many of each resource it might need to complete. So process 1 is saying I might need up to 1 copy of A, up to 7 copies of B, 5 copies of C. Right, so that's declared up front when the threads are running. So that's never changing. And then we have, this is essentially a snapshot of the system at some particular point in time where, say, we have these allocations. So process 1 currently has 1 copy of A, no copies of B and C. Process 3 currently has no copies of A, 6 of B, 3 of C, so on and so forth. And then we have the available resources that are not allocated in the system. So right now we have, say, 1 copy of A, 5 of B, and 2 of C. Questions on how this is set up? So what are sort of a few questions we can ask here? So first of all, based on this, how many resources are there in the whole system of types A, B, and C? How can we easily compute that, given the graphic? The information we previously had. Yeah. Right. The total number of resources in the system is simply what's available plus the total allocation of each of the threads. Right. So in this case, the resources is just the total plus the available. So we have 3 copies of A, 14 copies of B, and 11 copies of C. So now remember when we were talking about Banker's algorithm, we had this notion of what a process might need in the future. So how do we determine what a process might need in the future, might request? So let's say we're process 0, and right, the maximum they might need in order to finish minus what they currently have, right? So like P0 already has its max allocation, so it's not going to need anything in the future. It's not going to request anything. Whereas, say P1 might need up to 1 copy of A, 7 of B, 5 of C. It currently only has 1 copy of A, so it might request 7 copies of B, 5 copies of C in the future. Right? So this need matrix is just the maximum allocation minus the current allocations. So as we are executing and allocating resources, the allocation and the need matrix are changing. But they're all ultimately based on what the upfront stated maximum allocations were. And so then, of course, the question we're most interested in is, is the system in a safe state? And remember, the intuition for what we're doing here is we want to come up with some sequence of processes that even if they request everything they might request right now, we'll still be able to solve that. So what we can see here is this is actually a safe state because we can just pick some sequence here that works. There are potentially multiple sequences. But in this case, what's sort of the most obvious thread you can run right now? P0, right? Because P0 doesn't need anything more. So let's just say we run P0. Now P0 has 1 copy of C. So P0 has finished, releases its 1 copy of C. So now what do we have available to allocate? So what's our current available resources after P0 runs? Yeah. Right. It's just what we had previously available plus what P0 just released because we just ran that to completion. So now we have 153 is currently available. So now we can say run P2 because it only is going to request 1 more of A, which we have. Once it's finished, it's going to release all of its resources, so on and so forth. I won't do all the intermediate steps, but basically, P0, P2, P1, P3 is a sequence that we will be able to run everyone to completion, and they'll get all of their maximum resource allocations. Right? So as long as we can find one such sequence of this, then we're still in a safe state. And that's essentially what Banker's algorithm was doing by looking for a sequence of threads that we could run one after another that would ensure that we can actually do this. Questions on this? Okay. So, let's say now that process P1 wants, additional resources, and let's say that what it's requesting is, no copies of A, but 5 copies of B and 2 copies of C. So, right, so what Banker's algorithm is doing here is saying essentially, do we want to grant that request immediately? So remember, the idea is we want to determine, what the state of the system is after doing that allocation, and then decide whether that's a safe state or not. So if we actually do that, then let's say we do that allocation. So now we just gave 5 additional copies of B to P1, 2 additional copies of C to P1, and that, of course, decreases the available resources. So now we just have 1 available copy of A. So, right, so the 3 checks that the Banker's algorithm is doing here is, first we, of course, need to check whether there are enough available resources to do this allocation. Right, and clearly there were. We had 5 and 2 available previously, so we can actually do that. So that's sort of the first check. The second check is whether the process is actually allowed to request that many, which, it is. Clearly we're still under the maximum allocation of P1, so that's allowed. And so then the third question is, is this still a safe state? And so this actually is still a safe state because, we have one copy of A available, and that's the only thing we currently have available, but we can still make progress, right? So what can we run right now? Yeah. P2. Yes, yeah, sorry. Yes, we can run P2 here. I think this may actually supposed to be P2 there. Yeah, in any case, yes, we can now run P2 here because we have one copy of A available, and that's the only thing that P2 might actually need right now. Because it has one copy of A, 3 of B, 5 of C, and its maximum is simply 2, 3, 5, so the only thing it might need in the future is one more copy of A. So you can work out the detail of that, and this is still a safe state. So what Banker's algorithm is going to do then is actually say, yes, this is fine, go ahead and make that allocation. And then any future allocations, you're going to run the exact same procedure. And since every single time you're starting in a safe state, you're looking at an allocation saying, is it going to bring me to another safe state, in which case I'll still do it, or will it bring me to an unsafe state, in which case you can't guarantee that a deadlock might not occur. Yeah. P2 to P3. What do you mean by P2 to P3? Right. Yeah, because you can easily get into a situation where you request resources, and if you granted those, then if everyone requests the max, then you are deadlocked. You can't make any progress.
If you finish, if you do P2 and P3, P3 will just wait because you don't have any C's available. If you P3 will just wait until P2 finishes and then getting P3 the two C's. It'll still put it in the safe state because you have 5 C's at that point.
So you're saying if what's requested?
Well, he was saying if you do P2 and then P3, that would be unsafe, but P3 would only.
You mean if you execute P2?
Yeah. Well,
so I mean, if you execute P2, then you now have released all of P2's resources.
Then in which case P3's request would be perfectly safe.
Yeah, but if you try to execute that.
Well, no, because P3 would just wait on. If they execute them in parallel, P3 would request. If P3 requests the resources, P3 would just have to wait for the resources to be released by P3.
So if we execute P2 and then P2 finishes.
Well, no, he was asking if you executed P2 and P3 in parallel, would that create an unsafe environment? What's his question?
So are you not asking in terms of like what the algorithm is doing, but like in terms of?
I'm just trying to add, so if you went P1 and then directed P2.
So if you ran P1.
Yeah, you ran P1 and right after, like in parallel, and this might be a difference in understanding.
Well, but I mean.
Do you have to run P1 first and then P2, or can you run P1?
Are you talking about what Banker's algorithm is doing, or what the program actually runs? Because remember, P1 currently has this allocation, and it's possible that it could actually just finish with that allocation and be done. But the whole point of the Banker's algorithm is we're essentially assuming that it's going to request all of what it actually might need.
And then you go look at P2 given the fact that.
Right. So at some point, if P1 requests 2 more of resource B, right, because that could still happen.
Yeah, that's right. So you assume that once the resources are made, they're like reset.
Yes.
Okay,
Yeah.
that's right. Yeah. So yeah, then that case, P2 would be okay. P3 would not be okay.
Well, if P1 requests 2, P2 would be okay, but P3 would not be. if what happens?
If, yeah, so I guess if P3 tries to request C's,
Well, really, it'd be
tries to request
I mean, if P3 tries to request Cs, it's obviously not, resources are not available for that, so it's going, well, resources are not available, so it doesn't even get to the point of deciding whether it's safe or not. It's just not going to, because remember when we looked at Banker's algorithm, the first thing we were doing is seeing, first of all, is it allowable, but also, are there enough available resources? And if there are not enough available resources, then you're just going to wait until there are. Yeah, because the whole point of a safe state versus an unsafe state, that arises when there are sufficient resources to do the allocation right now, but that might put you into a state where down the line you might deadlock. So if there aren't sufficient resources available, you're never even going to have to check because you just can't do that right now. And similarly, if you're trying to exceed your stated allocation. Is that?
I'm just trying to help with it. I think I'm just confused a little bit about how resource or where the Deadlock thing. But I'm
Okay. Other questions? Okay. So let's just summarize this. So remember, we're talking about deadlocks where you have a bunch of threads or processes, and they can't proceed because they require resources held by another. And we talked about 3 different strategies for dealing with those. We have deadlock and recovery, which is sort of the least restrictive approach, where you're saying, I'm not going to do anything about preventing deadlocks, and then when they do occur, I'm just going to try to first detect them and then recover from them. Right, so that's the least restrictive approach, but breaking deadlocks is potentially unsafe. It's not clear what the best way to actually do that is without sort of indiscriminately terminating threads or programs. Second approach was prevention. So remember, this was sort of the most restrictive from the perspective of the programmer, where you need to write your program in such a way that deadlocks are impossible. And remember, the way you can do that is by ensuring that one of those 4 conditions does not hold. Because if one of those conditions does not hold, one of those 4 conditions we talked about, then deadlock is impossible. And then the third approach is avoidance, which is we're not being imposing as much on the programmer, but we're going to be doing runtime checks so that when you're asking for a resource, we're only going to allocate it if that puts us into a safe state where we can guarantee that a deadlock won't occur. And so, in practice, OSs essentially just use option 4, which is the OS itself doesn't really do anything for you and assumes that you, by yourself, as a programmer, will handle deadlocks on your own. Now, note that this means that, although OSs are not typically doing this kind of stuff that we've been talking about, it's not like, this information is not, the deadlock detection is not relevant anymore because, as we talked about, these types of questions are still present. They're just normally operating at the level of, the application that you write as opposed to, the OS avoiding deadlocks on your behalf. So I think I'll stop there, and next class we're going to start talking about memory management. So this pretty much wraps it up for processes and synchronization and scheduling and all that.